Perfect. So now, well, I mean, that stuff has already been hyped up quite a bit by Camelia, and I'm going to tie together now these pack-based ideas we've seen a bit with the variational stuff from before. And Badr is a researcher at CNIS and also a current collaborator of mine. I think I'm leaving you in good hands, Badr.
Okay, thank you. So, thank you for being here, and thank you to all the organizers of this very nice event. So, as Jan said, I'm going to talk about something you already heard today, thanks to Camelia and her very nice talk. So I'm going to talk about importance-weighted variational inference, and in particular the asymptotics. The specificity of this talk, when compared to the one of Camelia, is that we will really focus on the statistical properties of IWVI, and in particular, what happens when you optimize the bound using a data set. So this is based on a joint work with Randall, which is a professor at Télécom Sud Paris, and which is the former PhD advisor of Camelia, with Arnaud, which is currently at DeepMind and used to be at Oxford when we were starting this project, and Hugo, who used to be as well a PhD student of Randall. So yeah, before starting, so if you want to interrupt me at any point to ask for something, don't hesitate, just to say. Oh, yeah. Okay. Okay. So we try to present this project in a different perspective when compared to the one of Camelia. So we start with maybe the gold standard, or maybe the most famous estimator in statistics, which is the MLE. So we assume that we have a data set, which is assumed to be like a collection of IID random variables. So here the bold characters will characterize like a random variable. So we assume that all the data points are IID, so they're independent, and they all follow the same data genetic process, which is called P star and is unknown. And so we assume that we have a model that contains, so with densities with respect, let's say, to Lebesgue measure, and which belongs, which contains the data generating process, so that there is a true parameter that we want to estimate, basically. So the unknown theta star is the one we want to make inference and enrich. So basically, we can define very easily the MLE, which is simply the parameter in the parameter space that maximizes the likelihood of the data, which is, as a data or ID, the sum of the log densities evaluated at each data point. Okay, so very classical estimator. And actually, the MLE is a very nice estimator for a few reasons. The first one is the consistency of the estimator. So all those notions are asymptotic. So as the sample size goes to infinity, so we collect an infinite number of data. So the MLE is consistent, which means that as the sample size goes to infinity, the MLE recovers the true parameter theta star. The second one is the efficiency in parametric models. So here, you see the size of the parameter is D. So in the case of Camelia, she played a bit with that, and consider the asymptotic case where D is going to infinity. This is not the case here. Also here, D is fixed. So the estimator is efficient, which means that I will detail it in next slide, that it achieves the Cramér bound. And the third point is the stability under model misspecification. So I don't know if there is like a just like, let's say, a general way of quantifying this. Sometimes we talk about robustness. I think that it is not really a good thing to talk about robustness here, because the robustness is with respect to the KL, which is not a good metric to measure, for instance, if you have outliers. So basically, you have these three properties. So the first one is the consistency of the MLE. Okay, so almost surely you have the convergence of the MLE towards the true parameter. The second one is the efficiency, which means that, so under suitable conditions, the MLE is asymptotically Gaussian, centered at theta star, and with variance roughly the inverse of the Fisher information matrix divided by n. And when the data generating process actually does not belong to the model, then the MLE does not behave like badly. It actually converges to the closest distribution, to the parameter corresponding to the closest distribution to the data generating process within the model, right? So It's why I do not really like the name robustness, because the KL is a bad way of measuring like robustness, but let's say stability, okay? And in particular, it also has like an asymptotic normality behavior, but just you have a variance sandwich information matrix instead of the Fisher information. So, and there is one additional requirement that we want for an estimator, which is the tractability. And so basically the problem with the MLE, this is actually the starting point of importance-weighted variational inference in general, using in this context, in the context of latent variable models, which is that the MLE is not tractable. So, I mean, not tractable, not always tractable. And in particular, in latent variable models. So we consider a latent variable model with a joint density over X, which is the observed variable, and Z, which is a latent variable, okay? In this case, the density is simply the integral of the joint density when we integrate over Z, okay? And the problem is that in many models, so Camilla just gave us an example earlier, but this density will not be tractable. So computing the MLE is not feasible in practice. And so we need to resort to other estimators than the MLE. And as you guess, like there are actually two related problems. The first one is that, so it's not directly related to the computation of the posterior, but the computation of the MLE, sorry. But if you look at the posterior distribution, you can see that the posterior distribution relies on a normalizing constant, which is intractable by definition. Okay, so you cannot compute the posterior. This is the first problem. And this problem, which is at first not related directly to the computation of the MLE, is actually related to the problem of computing the MLE, because if you want to compute the MLE, you need to compute the gradient, and the gradients rely on the posterior, okay? And you don't have access to this posterior. So if you could sample from it, you could estimate this gradient very easily. This is not the case, okay? So actually you have at first, let's say, one problem, which is computing the MLE, but in fact, you have two related problems, computing the MLE and computing or sampling from the posterior distribution, right? And so this is where variational inference comes to the rescue. Actually, VI addresses both points, okay, by just like, so Camelia introduced that very well this morning. So by actually the target of optimization in VI is not really the log likelihood, but a lower bound on the log likelihood. And this lower bound involves an approximation of the posterior. So actually, you don't have just an optimization of a theta, but an optimization of a theta and the approximation of the posterior, with the idea that when the lower bound is optimized, you get a good approximation of theta star and a good approximation of the posterior. This is basically the idea, okay? And so you have really two steps. The first one is, I want to derive a lower bound on the log likelihood that I will optimize with respect to theta and to the approximation of the posterior. And the second step, which will not be the focus of this talk, which is the optimization aspect. Okay, so we need to ensure that the bound that we derive as the objective of optimization is tractable. We can optimize it, right? So Camilla actually talked a lot about that aspect, the second one. I will shortly, briefly talk about that, but this is clearly not the main aspect of this talk, and we will really focus on the asymptotic properties of the estimators maximizing the lower bound, right? And so let's start with like the first lower bound that we have, so the elbow, the evidence lower bound that Camilla presented this morning. So we use as an approximation of the posterior this kind of distributions. Okay, so this distribution is conditional on the data point we consider. Okay, if we have a posterior P of Z given X, we approximate it using a distribution Q of Z given X. Okay, and we consider a lot of different distributions. Okay, and these distributions are parameterized by a phi. The parameter phi is really distinct from the parameter from the data point X. Okay. So, for instance, you have just like this example where you see that the phi and the x have a distinct role, or you have like the very nice picture that Camilla told us with like many equations that you can just use as an approximation of the posterior, right? Now, so yeah, maybe one thing that I didn't say is that I tried as much as possible to match Camilla's notations for this presentation. It's not very successful, so there will be some slight differences, okay? The first one is that she loves the integrals. I will use a lot of expectations instead. For one reason, because sampling will appear at some point in the talk, so I think it's simpler to use expectation. So we just write the log density given an observation as a log of an integral. So given that if the support is well-defined, is right, then I write this integral as an expectation, and now I can use Jensen's inequality because the logarithm is concave, so that I get this lower bound, okay? And from this lower bound, I have the following objective, which is called the elbow. So I just sum over all the data points, this lower bound. So this is indeed a lower bound on the log likelihood. The log likelihood is just obtained by summing all the log densities. And if I maximize this lower bound with respect to theta and phi, then I get my VI, my elbow estimator, okay? So this is the first thing I can do. I can define a new estimator that maximizes something that is tractable, okay? So now that I have derived the bound, I need to ensure that the bound is tractable, okay? So you have the optimization of this bound, and Camilla already said what you need, actually. So you just like invoke the reparametrization trick. So basically, what does that mean? It means that the sampling from the distribution Q phi given X is the same thing as sampling first from a fixed distribution Q and transforming the sample, okay, from let's say epsilon to Q, to Z, sorry, okay. So you have so for instance, just imagine that sampling from a Gaussian with mean M and variance sigma is the same thing as sampling from a standard Gaussian and then from writing, considering M plus sigma times what you sample, okay? This is very simple. And using this, the nicest point is that this expectation can be, with respect to Z, can be written as an expectation with respect to epsilon. And now that this is done, what is nice is that you can write all the gradients. You can, swap the gradients and the expectation. And then you have an expectation. So this expectation can be just like approximated by just like, so here, one sample using one sample, but Monte Carlo sampling, you can use a lot of things. So this actually gradient is tractable. And if you just take a look at the gradient with respect to theta, not phi, you actually have exactly this formula, but with the approximate posterior instead of the posterior itself, okay? So you just actually made optimization of the log likelihood feasible, in a sense. So this is not, once again, this optimization part is like not the main point. So if you have any question, please come us here and you can just like answer a lot of questions. And just like just to say that this is really like a feasible estimator that you can compute. And what we'll do today is to investigate the behavior, the asymptotic behavior of this, not this estimator, but a relative, okay? And now I will try just to motivate and to convince you that this estimator is actually not that good in a sense. So actually, just a reminder that the MLE can be defined that way, okay? So here, instead of saying we maximize the log likelihood, we say we maximize the log likelihood divided by n. Why I'm saying so? Because now we have an empirical average, and an empirical average, law of large number, is expected to converge to an expectation. So of course, there are some technical assumptions that ensure that, but we expect, so the MLE, to converge to the maximizer of the expectation on the right-hand side, okay? And the maximizer of the expectation on the right-hand side here is just theta star, okay? So this is very, very simple, actually. We expect, when we maximize the log likelihood, to converge to the truth. But now, if we take a look at the elbow that we just defined, actually we can rewrite, so this is very basic, just like algebra, we can rewrite this expectation like that. So we don't maximize the log likelihood, but we maximize the log likelihood minus the KL between the proximate posterior and the posterior itself, okay? So now, just imagine, so you have the log likelihood, which is maximized. So in expectation, the expected log likelihood is maximized at theta star, and the expected KL is minimized because it's a minus, is minimized when this is equal to that. So imagine that you have a phi such that the approximate posterior is equal to p theta star given x. Then in this case, this will be equal to 0. So this is minimized, and this will be equal to the log of p, the expectation of the log p theta star at xi, which is the maximum. Okay. So if this condition is satisfied, then you have the maximizer of the expectation of that, which is exactly theta star and such a phi. Okay. So I'm saying this because actually there is a possibility that when targeting this objective, you recover exactly theta star. But the condition means that you have actually an approximate posterior in your variational set that exactly matches the posterior. And basically, what does that mean? That means that either your posterior is very easy to compute or to sample from. So actually, you didn't have any problem at the beginning. So you can just perform MLE. Or it means that your approximate posterior is very complicated. And so doing VI is not a good idea because your set of tractable approximations is not that tractable, okay? So basically, when you are in a situation where the posterior is very easy to compute and the approximate posterior is very nice, just a Gaussian, for instance, then this is not likely to happen. And so actually the limit of this elbow estimator will not be theta star anymore. So actually the point is that in general, the maximizer of the elbow, at least when you look at the theta parameter, is not expected to converge to theta star. And so this is why there is a need for tighter bounds in order to achieve the consistency. So once again, I'm not saying that you should use more, just like, because we will take a look at the IWVI, as you guess. I'm not saying that a tighter bound is always better. I'm just saying that statistically, in theory, if you increase your number of samples in IWVI, then it's very likely that you will get a better and a better estimator. Okay, from purely if you want to estimate it. Okay. And now, I'm just now introducing IWVI, so you know it. So a slight difference. So Camilla said like the I-way bound. We say the I-well bow. This is exactly the same quantities, just like a different terminology. So we just write that the log likelihood, the log density, let's say for a fixed observation is the log of the expectation. And actually you just use the linearity of the expectation so that actually the expectation is equal to the average of the expectation itself. Okay. And then you use Jensen's inequality here to get this lower bound. Okay. So this objective is still a lower bound on the log density, but it is a tighter one than the standard elbow, because if you see the empirical average as itself an expectation, you can use, once again, Jensen's inequality, put the log inside the expectation and get the elbow, right? So you have the two bounds. So this is a lower bound on the log likelihood, and this is an upper bound on the elbow. So the elbow, whatever the number of samples that you use, is a bound on the log likelihood, which is tighter than the elbow. So if you listen to the talk of Camelia, you didn't see any K, you had a capital N. So this is exactly the same quantity. My K is her capital N, right? So I chose to match the notations in my paper rather than in hers, okay? But that is exactly the same quantity. And so we now define our estimator, the I-Welbo estimator, let's say theta tilde and phi tilde, nk, as the maximizer of the I-Welbo when I sum over all the data points. So Camelia brilliantly talked about how we can compute this one. So you saw that you had exactly the same gradients, but using importance weights typically. There is no additional difficulty really when compared to the standard elbow. So you have many tricks, but once again, this is not the main focus on this paper. What we'll really do today is to study the asymptotic behavior of that estimator as the theta tilde, right? And so now, just before talking about the asymptotic behavior, I would like just to recall a few properties that Camelia already introduced this morning. So here, this is the only slide where we don't have data, we only have an observation X. This is a fixed observation X. So the I-Welbo here is actually this quantity and not this evaluated at the data point. Okay, just like imagine that you have one observation. What can you say? You can say that first, if you consider k equal 1, k equal to 1, then you only have the elbow. Okay, so the I-Welbo is an extension of the elbow. The I-Welbo is actually a family of lower bounds, which is monotonic in k. So the larger k, the tighter the lower bound. Asymptotically, so when you increase the number of samples k, then you converge to the log density. Okay, so asymptotically, the I-Welbo will converge to the log likelihood. And you can even quantify this gap between the I-Elbow over the k and the log density. And it is actually simply equal to 1 over k. Okay, so if k is large, the difference between the I-Welbo and the log likelihood is simply key. So there is Alexandre. Let's admit it. Great. Okay, so I just, so I was like, so here, what do we know? What can we say now? That the I-Welbo is converging to the log likelihood at rate 1 over k. And here you just have like the variance of the importance weights. So I think that Camelia told about relative weights this morning. This is exactly the same quantity. Okay, so this is the ratio of the posterior of its approximation, which has like expectation equal to 1. Okay, and so why do I introduce this? Because what is expected now is that if k goes to infinity, the I-Welbo goes to the log likelihood. So maximizing the I-Welbo is equivalent to maximizing the log likelihood. So it should be expected that asymptotically performing IWVI is equivalent to performing ML. Okay, and so this is exactly the question we'll try to answer. Is it equivalent performing IWVI asymptotically to performing ML? So what does that mean? Being equivalent, it means that achieving consistency and efficiency, right? You have two aspects. In general, consistency is included in efficiency, but let's do one step after the other. So this is the question we'll try to answer. Is IWVI as good as the MLE in terms of statistical performance? So it's just a reminder. Informally, the MLE is efficient, which means that it is asymptotically a Gaussian centered at theta star with the sandwich asymptotic variance. And now we will perform an asymptotic study and an asymptotic analysis. But as I told you, the asymptotics is in K, as Camelia did. But now we have the data points, okay? And we have another number f on the data points. So the asymptotics is at the same time in K and in N. And so we have double asymptotics. So it's different to what Camelia had. Here, the asymptotics are in the number of samples, important samples, and number of data points. And the fact is that when you have double asymptotics like that, you should handle like the convergence with slight care, because it means that here n goes to infinity, but does k go to infinity with n? Do they go to infinity just like independently? Is there like some rate of convergence or something like that? There are many questions that actually appear. And to be completely honest, before starting this project, I wasn't really aware of the literature that existed on that. And actually, I mean, we did not really start from scratch. Actually, there is a community, so the people from econometrics that actually know pretty well this kind of estimators and this behavior. And actually, they just like for maybe 50 years, they have been studied just like very related estimators, and one in particular, which is called the maximum simulated likelihood estimator that I will introduce. And it has been very popular maybe since at least the early 80s. So the idea is very different, but very related at the same time. So you just start from a joint latent variable model, so with the infractable density. So now I write it as an expectation again. The only difference is that here you don't have an approximation of the posterior. You just fix a proposal distribution Q. Okay. And what do you say? What do you know? You know that actually you cannot compute this exactly, but what you say is that, okay, I cannot compute that, but I can estimate this. So if I can sample from Q, then I can say, okay, I just like sample a number of latent variables Z1, Zk, and actually I just consider the empirical, the Monte Carlo average, okay? So I have very easily an approximation of my log density, of my density, right? So this idea is very completely different from what I did previously. But in some aspects, you have some similarities, consider expectations, we have an average, and so on. And now, the fact is that if I want to perform maximum likelihood, the problem is that I cannot compute the density. This is not a problem, actually. I cannot compute the density, but I can estimate it. So I estimate it using like the latent. So for each data point, I sample a set of k latent variables. I approximate the exact density by its Monte Carlo approximation, and then I consider the sum of the log. And I'm done, actually. So now I have defined a new estimator using simply Monte Carlo sampling. Okay, basic Monte Carlo sampling with independent rows. Okay. And you can use standard optimization techniques, so with some ad hoc methods, let's say, to maximize this quantity. So this is an objective which actually is very close to the one that we have, with mainly three differences. The first one is that in our case, we consider the expectation over the latent variables, whereas the MSLE, so maximum simulated likelihood estimator, does not maximize an expectation, but what is inside the expectation, okay? So in a way, there are two sources of randomness in their estimator, one coming from the data points, the xi's, and one coming from the latents that are all sampled, okay? In our case, there will only one source of randomness, which are the data themselves, right? The second part is that in their case, there is no approximation of the posterior. Q is a fixed distribution, even though it can be just like fixed, like using some tricks, but basically it is a fixed posterior, which is not optimized. And when they want to find a good proposal Q, in general, they really separate this aspect, choosing a good Q from the optimization of a theta. In IWVI, the problem is joint, actually. You jointly maximize our theta and phi. These are, I mean, this is only one problem. And the third part is that actually I mean, people in machine learning use this with very small tricks, and computation is very easy. I mean, for the people in econometrics, it's been a long time they've been using this. You didn't have even like very powerful computers at that time, so it's not very comparable in the optimization aspects, okay? But still, you have two very similar estimators, okay? And so the question is, what is the behavior of this MSLE? So the first question, is the MSLE consistent? And actually, the answer is very simple, yes. As soon as n and k go to infinity, okay? So this is a very simple answer. What if, I mean, even if the convergence of k to infinity is logarithmic in n, then you will get consistency, okay? So you have some conditions which are a bit strong, actually. So actually, so the literature comes back to the 80s. And actually, there are sometimes a few very strict, strong conditions. So this one, for instance, kills me a bit, like having like the density which is strictly bounded away from below. It's like, seems very strong to me, but still under some conditions, you can have like the consistency of your estimate, right? Regarding the efficiency, actually, the answer is not that simple. Actually, it's just like, what really matters actually is how fast k goes to infinity. The answer is not yes or no, it is efficient or it is not efficient. Actually, the answer is if k goes to infinity fast enough, then yes, you will get the efficiency. Otherwise, you will not get the efficiency. Okay, so you have, in a sense, some threshold for k over which you will get efficiency. And the threshold is the following, is the square root of n. So as k and n go both to infinity, if k go to infinity faster than n, square root of n, then you will get the efficiency. Otherwise, you will not get the efficiency. So this is, in a way, you typically have two regimes, or even three, to be clear. The faster and no faster than square root of n that characterize the consistency, the efficiency, sorry. And what happens below this threshold? So actually, if you're exactly at this threshold, which means that if actually the number of samples goes to infinity exactly at rate square root of n, then you still get an asymptotically normal estimator, but actually you have an asymptotic bias. So basically, the square root of n times theta hat minus theta is asymptotically normal with the right variance, but with some bias, okay? However, if k rises slower, so strictly slower than the square root of n, then you don't get efficiency at all. I mean, you don't even have a normal distribution, okay? So you can characterize it with some nasty form, but you don't have anymore a Gaussian distribution, right? So starting from here, we could just like have a conjecture, which is that, okay, maybe we have exactly the same thing, which is that IWVI is consistent as soon as n and k go to infinity together, and IWVI is efficient as soon as k goes to infinity strictly faster than the square root of n. And actually, the answer is no. And it's even more complicated than that, because actually, so a few years, so maybe almost 20 years ago, so there has been a paper by Song and Geyer, which actually does not even cite the previous papers, which is a bit just like maybe two different literatures, which study exactly the same estimator. So exactly the same one with one difference, which is that what they say is that, okay, instead of sampling a set of latent variable for each data point, I just sample once a set of latent variables, and I use this set of latent variables for each data point, okay? So the only difference is that here you do not have the index I, okay? So here on the top, you have n sets of latent variables. Here you have one set of latent variables. So this is only a slight change, actually. So having independent rows or overlapping rows, but actually it changes the whole story. So regarding I will just like put the summary. So regarding the consistency, it's exactly the same thing. So if k does not go to infinity, you don't have consistency. If k and n both go to infinity, you have consistency. But the story of efficiency is very different. And basically, you don't need a growth of k faster than square root of n. You need a growth of k faster than n now. So your regime of efficiency is much smaller than when you had independent rows, right? Because you need, I mean, a much larger number of samples. But it does not really mean that this estimator is worse than the first one, than in the case of independent rows, because actually the estimator is always normal. So whatever the rate of growth of k, you always have a normal distribution asymptotically, which is unbiased. So what that means is that actually, basically, maybe I can write in the case of overlapping rows. Basically, the estimator is asymptotically always equivalent to a Gaussian, okay, which is centered at theta star, and with variance, which is like, so the variance of the MLE divided by n, plus an additional variance divided by k. So if the growth of k is faster than n, then this vanishes and you get the efficiency. If k is exactly at growth n, then it is not optimal anymore in the sense that the variance is higher, then this one does not vanish. And if the growth of k is slower than n, then this one vanishes and it only remains this term, right? So actually it's very useful to have, the first estimator is, with independent rows is very desirable because you have a much wider range, much wider regime of efficiency. But still, when you use a small number of samples, of important samples, then it may be preferable to use this one. So you don't have a very unique answer. Is it better to use like independent draws or overlapping draws? Okay. So this is what, to the best of my knowledge, so everything that I learned from this kind of literature, which is related to the IWVI. So now I'm back to my problem, which is that actually the IWVI looks like both of them. Because here we have an expectation. So actually what changes in the two definitions of the MSLE is the index. Is there the I in the index of the latent rows? But now, as you have an expectation, you can write the I in the index or not. It does not change the definition. Okay, it's exactly the same thing. I could even write something else, a C, a D, or wouldn't change anything. And so it's a bit difficult to understand whether, so it seems like the consistency should be fine, okay? In both cases, both are efficient as soon as or consistent, sorry, as soon as n and k go to infinity. So it is very likely that my estimator will be consistent as soon as n and k go to infinity. But which behavior is the right? I mean, is the asymptotic behavior of IWVI the one of the MSLE with independent draw or overlapping draws? So in other words, is there a threshold over which we achieve consistency? And if the answer is yes, is the threshold rather square root of n or n? So to answer this question, these two questions, so the first one is there is no, no suspense. Well, the answer is yes, of course, as soon as n and k go to infinity together. And actually the conditions are very, very light. You just need the conditions that ensure the consistency of the MLE. And you just need the existence of the KL between the approximation and the posterior for any phi and theta. So I'm writing like a variant because in general, you need the integrability, so you consider the positive part, but it's exactly the way you define the KL. Okay. So for that, this is a very light condition. Typically for the MSLE with the independent rows, you need to have like the boundedness from above, which is a strong condition. And even in the case of Geyer and Sung, the condition is a bit stronger. So for that part is very, the problem is very simple. The question is very simple. The answer very simple. It was expected, and you have a very simple answer. But the answer is a bit more complicated in the case of efficiency, because you have two different regimes: the independent one, when you have the threshold at square root of n, and the overlapping one, when you use only one set of latent variables, where the threshold is n. And so the question is which threshold, if there is one, is the right one. And actually, the answer is none of them. And actually, so you have two questions. Is there a threshold? And if there is a threshold, is the threshold square root of n or n? Actually, there is a threshold, but the threshold is between square root of n and n. And actually, what really matters here is not the result in itself, but the conditions that make it happen. Because, so it's not something that I told you, but you remind like the slide with all the properties of the IWVI. I don't really tell you what are the conditions that are needed to ensure that. So typically you assume that the importance weights have some moments. Okay. So typically in the Taylor development, you have like a paper with a 6 moment, another one with infinite moments. And basically what is needed is the existence of some moments, some fixed number of moments. You would approximately have the same assumptions when considering the MSLE. You assume that the log simulated likelihood have some moments which play the role of the log importance weight. Okay. Actually, here it is important not to say, okay, we have an infinite number of moments. We have 3 moments for the log importance weight. We have 4th moment. Why so? Because the rate, the threshold, depend on the number of moments that you have. So if you have a lot of moments for the logarithm of importance ratio, then the threshold will be very close to square root of n. At the opposite, if you only have a variance for the log of the importance ratio, or so 2 plus something, then you will be much closer to the n threshold, okay? So in the analysis, it's very important to be careful at the assumption that you have, because it's not even an assumption, like it's the nature of your problem. If you have a 3rd order moment, then you will have, so it's not very explicit here, but you will have a very large threshold. And if at the opposite you have like, I don't know, just like 1,000 of moments of moments of for the 1,000, that you will have a very small threshold, okay, very close to square root of it. So formally, these are the typical assumptions that we put. Those that are needed for the efficiency of the MLEs. The second one is the reparametrization. So we assume that we can reparameterize the variational distribution. And the third one, basically, I mean, the remaining is that we define the importance weights, so expressed with respect to epsilon and not z. And we assume that the logarithm of the importance weights have some moments, okay? And basically, so we need at least a moment of variance, okay? And something more than a variance, so something of order 2 plus something. So these 2 plus something is the moment of order alpha. So once again, I used a very wrong notation. There is nothing to do with like the alpha of Camellia, okay? We don't have like, we only have the KL here, so no connection with the previous alpha, it's just like the order of the moments. And actually, we need a bit more than that, because just like, so I did not do like Camellia, I did not put a screenshot of a very nasty formula, but you have a lot of just like, it would have been needed to just like put all the precise formulation of the assumptions. But just like, keep this in mind, this is the main message. And if you, under these assumptions, then what you have, so you have a threshold, which is of order n to the delta divided by 2, where delta is the number, which is such that 1 over alpha plus 1 over delta is equal to 1. So here alpha is assumed to be larger than 2, so delta is between 1 and 2. So delta over 2 is between 0.5 and 1. So this is between the square root of n and n, okay? So the answer is the following. We have the consistency, always, I mean, as soon as n and k go to infinity. And we have the efficiency, provided that k grows faster than some threshold. And the threshold is between square root of n and n. So in a way, you have kind of all the possible thresholds between square root of n and n, sorry, kind of an interpolation between these two extreme settings, which happened for the MSL, okay? So this is the main message of the paper. And one more, I would like to just like add one more result. So in the block here, you have like what I told you. And the last thing is that, as I told you at the beginning of the talk, I said that there are actually two problems. The one which is estimating the theta star, but there is another one, which is that we cannot compute the posterior. And IWVI in general, so not necessarily IWVI, VI in general solves the two problems at the same time. So provides a lower bound so that you can estimate theta, and it provides an approximation of the posterior. So here, what can we say about the posterior that we have, the approximation that we have learned? And actually, just to understand, it's a reminder of what I told you previously, the Taylor expansion of the IWVI. What does that say? It says that as k goes to infinity, this goes to this. So what is expected is that the maximizer of that converge to the maximizer of that, the expectation of that, right? If we expect something, we expect that. And for theta, this is actually the case. Remark that here, there is only a dependence in theta, not in phi. But the question is a bit more complicated in phi, because as k go to infinity, this is 0, but there is no dependence in phi in the 0 order term. So basically what we could expect is that the IWVI, I mean, the maximizer of the IWVI will converge to the minimizer in phi with respect to phi of the first order term, of the dominant term, actually, in phi, okay? So what we could expect is this convergence. And as theta has converged to the true one, we can say here, it should be the true one. So ideally, if like it's possible, this is what we could expect. And this is actually the case. So under some conditions which are pretty mild, I mean, we need like some moment condition of our order like 4, maybe it's like for technical reasons. But what is interesting to notice is that actually there is another way to rewrite this variance. I don't know if you got it, but it's just like exactly equal up to a constant to this, which is the chi-square divergence between p theta star in Q5. I mean, this is exactly equal to that up to a constant. And so what does that mean? What does that mean? It means that asymptotically, when you're performing IWVI, you're actually learning the true parameter theta star, and you're learning an approximation of the posterior, which is the closest to the true posterior, so the posterior at theta star, which is the closest, but with respect to the chi-square divergence. So this is something that is actually, for people that are just like familiar with the Monte Carlo literature and importance sampling, it may be not very surprising, but at first, I mean, because this is the minimizer of the variance of the importance weights, but actually it means that, in fact, when you're performing IWVI, you're not really minimizing the KL. What you're minimizing is the chi-square divergence, so which is a different objective. So in a way, I think that's just like it's clarification of something that is worth it, I think. And so this is all I wanted to say. So just like a summary of what I said. So asymptotically, when n and k go to infinity, then IWVI is equivalent to the MLE, provided that k is larger than, grows faster than the threshold that I talked about. And the second part is that actually the asymptotic approximation that we compute is exactly the closest distribution to the true posterior in chi-square divergence. Thank you.
You now have quite a lot of time for questions.
Great. Yeah.
Thank you. I have a couple questions. Okay, so my first question, maybe can you go back to basically comparison between this maximum simulated line frequency estimation and IWVI, right?
Maybe
Next.
this one. Yeah, this one.
Yes.
Okay, great.
Okay. I'm trying to understand the impact of this expectation time you have here, right? In addition to this just simple Monte Carlo. I'm saying that in practice, right, you actually implement IWVI using Monte Carlo, which means actually we are doing, let's say, this closer to this a simulated likelihood case, except that you are simulating from a X index proposal.
Yeah, exactly.
Right?
Yeah.
So why did you actually study this expectation case instead of studying, let's say, the practical case?
So repeat just a question.
Don't use expectation.
Which one?
This
one?
Sorry, this IWVI bound there. You
Okay.
have expectation of the ROI, right?
Yeah.
So in practice, you do something.
Yeah.
So this basically means actually, I think what we implement is actually something looks like this independent MSLE, except that you are using X index proposal.
Yeah. Okay.
So yeah, so what is the result for that?
Well, actually, the difference. So maybe I just like to be clear. What you mean is that in practice, you don't really, in the optimization process, you don't use an expectation, but you approximate the expectation using a Monte Carlo average, right? Yeah. Well, the difference, I mean, in theory, is that at each optimization step, actually the samples that you draw are really different. So, in a sense, the two estimators are not the same at all, in the sense that in this estimator, so the first one, the Z are fixed once for all. So you sample them at the beginning of the process, and what you optimize is so the objective, but with the same ZIs at every step. In the IWVI optimization framework, you still use it's just used to estimate the gradient at each step of the optimization process, but these are not the same ZIs that are sampled, and just so I didn't present the numerical simulation, because they were very poor, but even we did not really, I mean, in the numerical, yeah, sorry.
Samples the duration stack that makes a difference. The
Yeah,
yeah.
this is it. Yeah, this is the main difference, and the second difference is that actually there is a file that makes it possible to just like to reparameterize it at each step. Actually, it is possible for people. What people do sometimes in the MSLE is to use a reparameterization of the Q, but which depends actually on the theta, not on the phi. You know, if you see what I mean. So it is still a bit different, but in practice it works because the MSLE is a bit more involved to implement.
Again, so goes back to your chi-square
Yeah.
result, right? So right, so people say that this IV bug will converge to the marginal likelihood when you take K equals infinity, right? So that is basically proved in the original paper.
Yeah.
Right? So you also show this kind of Taylor expansion, right? Do you say a bit about why? Maybe when your result actually somehow contradict to the original derivation, right? The original derivation from the IWVI paper really tells you that when K goes in infinity, you get back to the marginal likelihood, right? And then correspond to optimizing the KL, PQ.
So to be clear, it's not like the result that you mentioned is not. I mean, we did not prove it again at all. Just like we really use the one that has been proven is like in the original paper on all the others. Actually, well, so if I go back to this slide, the one with the elbow, yeah. So this one. Actually, the fact is that I would say okay with what you say, with what you're saying. If I mean the fact was that we typically had I mean typically here with what we're saying is that you minimize the log likelihood minus like the sum of the KL. So this in a way motivates the fact that here you really target the KL in some sense. The fact is that as you maximize this at the same time as you're minimizing this, here you don't really target the true one, P theta star, actually. But to the best of my knowledge, there is no such formulation in the IWVI. And so the KL does not really appear explicitly at any point in the IWVI. So yeah, I mean, it may be surprising. I don't know, but I mean, I agree. It may be surprising at first, but to me, there is no clear reason why the phi that you're learning, the approximation that you're learning, should target the posterior explicitly in KL, because at no point it appears in the objective of the IWVI. I mean, it's because typically you have, when you don't have latent variables, you explicitly target the posterior, you know that. But in the case of latent variables, it's not an explicit projection of the posterior towards the only way it appears is in this projective. And actually, if with the elbow suit, it appears at some point, but wrongly, because you have a log likelihood on top of that. But with the IWVI, it does not appear anywhere in the objective. So, I mean, so I used to work on a VI not related to latent variables. So to me, there was this relationship. But when you look at it, it surprises me, but I don't think there is a clear contradiction. I'm not sure of. So I don't know if this answers your questions completely, but yeah, actually it's like, so I'm not just like, I don't come from the importance sampling literature. So to me, like minimizing the chi-square is not very natural, but it seems like for people that are working with importance weights, like that are trying to minimize the variance, minimizing the chi-square is like pretty normal standard. So I would tend to agree with you, but I wouldn't say that it contradicts actually what should happen in a sense. But yeah, Camilla. Which one? Which paper? The one with the G-reg or? Yeah, okay, I get it. Just like, yeah, with the signal to noise ratios, right? Okay. Okay. So, thank you, Camilla. Yeah.
The
assume the SI are independent.
Yeah.
I'm wondering what if they're dependent. So imagine a heat pump model and your SI are observations, and that is your hidden states. And what's going to happen? Are you still have the same conclusion?
That's a good question. I don't know. I just like went out on the paper just like a week ago that did the same work as Geyer and the Sung and Geyer. So you know the one with the in the overlapping regime. And what this just like the paper is extending the, I think that they are tightening a bit the assumptions, but mainly they're extending the analysis of Sung and Geyer to Markov chains basically. So I mean, from a technical point of view, it should be extendable. They get exactly the same result as the one of Sung and Geyer with an additional assumption, and they just like remove others. So it should be feasible, but definitely the tools should be a bit different. And I don't have the answer to the question now, but it's like, I mean, formally it should be feasible without. I'm not saying without problem, but it should be feasible. So yeah. So the typically the result of Geyer, Sung and Geyer should exist because I haven't read the paper, so I don't want to say anything. But someone just like addressed the problem, just like maybe 5 years ago. Yeah, I should have on my phone, so I will just tell you after if you want. Yeah.
Stupid question. Can I interpret your results to mean that maybe I should, so if I have a reparameterizable variational family,
Yeah.
should I perhaps just draw my epsilon i's once and for all? And then I would be in the regime of that previous slide, like the independent MSLE, and then I could be guaranteed of being in this K only has to grow faster than
So the first one you mean? Yeah, exactly. Exactly, actually. It's what it means. But I haven't seen people like drawing things once for all, to be honest. But in theory, I mean, just like from a theoretical point of view, you're exactly right. If you just like sample your theta once for all, you would be in this regime. Your epsilon, sorry, once for all, you would be in this regime.
This was, but it was an accident. It's like a button, I thought. So I went back and did what everyone else did.
Yeah. So once again, I'm saying in theory because in practice, so I implemented them just on very simple examples, so just like very basic ones. So you have a likelihood, so a conditional likelihood of x given z, which is Gaussian, and z is like follows a Bloomberg, something like that. And actually, for instance, this one, which should be just like better in small regimes, is always much worse than this one. Actually, it's like, I think the problem is that asymptotically doesn't mean anything in practice. So you're never really in an asymptotic regime. So I haven't implemented them in like very large models, but I can tell you that in for simple models and in small regimes, like in practice, it looks like something asymptotic, but you have like the factors that are like present, which doesn't say something really. So in theory, yes, but I think it's in theory.
Thank you.
Yeah, so
Jeremy, that point. So I think maybe why this doesn't work in practice as well is that when you sample your gradients in unit every time, it has a regularizing effect that's well studied, right? So the loss landscape in theta for the kind of models you're normally looking at with VAs is horrible. So you actually want to average out all the jaggedness because otherwise your loss might look like this and you don't actually get anywhere useful. So
okay.
I'm afraid that's all the time.
Yeah.
Questions. Thank you very much.
Thank you.